So if I've done this correct, which there is no guarantee, you should be looking at question 5. Does that look good? Right. So I just want to show you what the questions look like, and we'll do this one in total. But basically, you've got a story in which you're going to conduct a hypothesis test. I was looking online for some good data, but I just couldn't kind of get it the way I wanted. So I gave up on that. Maybe I'll find some good data and tomorrow. But in this survey, if you remember the story, they had some money in a wallet, and of 93 women, 86 of them said if they found money with a wallet in it, they would give it back. They'd return it in some way. And 52 out of 75 men, because they are more honest, said that they would do the same. And we are going to try and test the hypothesis that women would return the money more often than men. So that's kind of what it is. All the information is there. There's the 86 out of 93 women. Here's the 52 out of 75 men. Here is the significance level. And they even go on and tell you population 1 is the self-identified women and 2 is the men. So hopefully you can just read a story, and from that you get the gist of it. So this is the gist of that question. What you're looking at is 86 out of 93 women, 52 out of 75 men, significance level of 5%. Now I'm going to turn these guys into decimals, and I'm looking around for accuracy, 2 decimal places, so that's what I'll do. 86 divided by 93 is about 92%, and 52 divided by 75 is about 69%. And we are now going to do the difference between them, which is 0.92 take away 0.69. And that's 0.23. And I know from people communicating with me that WebAssign is very, I don't know what the word I'm looking for, inconsistent with rounding off. And so if you get a question that at the end of the day you think it's 0.12 and they say it's 0.13, you are correct. I'm sure you're correct. I just think you've just get caught up with WebAssign deciding to, go this way by rounding off and not that way, because that has happened, right? You shouldn't lose points for that. So all you do is you tell me, and I can go in and fix it. I've tried to set it up so that it had a tolerance level, but it seems to ignore that setting. I tell it, give or take 1%, it's still right. Makes no darn difference. It still tells you you're wrong for some reason. So maybe I'm not doing it correctly or something. Anyway, we've got this guy. Right now, I'm just calculating all the numbers that we are going to be using. So the standard error is P1 hat, Q1 hat over N1. This guy here over N2. And we're just going to do that on the calculator as well. So I've got a square root. And 92 times 0.08 divided by 93 women, and then 69 times 31 divided by the 75 men. And that comes out to be 0.06. I'm sticking to their 2 decimal place then. And we should be ready to set up the hypothesis test. I want to keep all these numbers separate. So let's do the bit that's pretty general. Your null hypothesis is written down as the difference between them is 0. So we don't write P1 equals P2, but that is correct, it is. To keep WebAssign happy, we're writing it like this. And we were asked in this story, is there any evidence to prove that women would do it more than men, as you can see here? So P1 take away P2 is going to be greater than 0. Right. Now, you need a z-score. And it's P1 hat take away P2 hat over the standard error. So it's 0.23 divided by 0.06. And I get the answer. 0.23 divided by 0.06. I get the answer 3.83. Now we're going to get the p-value. And that's the probability that you get a z-score. Bigger than 3.83 or less than 3.83?
Bigger.
Whatever that says, this is saying the same. Now, this guy gets done using salt, and I'm clicking on the salt thing again, bringing it over here, and there we go. So let me show you that so we can just get more practice at it. Window out of the way. Looks like this. Right, is this a right-tailed or a left-tailed? Z greater than 3.83. Right-tailed or left-tailed? Because I have to pick one of these things over here, right?
Right-tailed.
Okay. Now, if you go over here, do you see how the little greater than or equals is pointing the same way that we wanted? And this number is going to be 3.83. And the answer I get is a tiny answer, which is a good thing for a p-value, because that tends to mean something significant is happening. And it's 0. God, my scanning 1, 2, looks like 4 zeros. Yeah. We have got to the point where we found the p-value. Then we do our test. Here's our p-value. Oh, by the way, I will turn that into percent. It's still tiny. And is our p-value less than the significance level alpha? Is our p-value less than 5%? And yes, it is. So what we would be typing in would be, well, see what they want you to do here. So we just, it's little tabs that you pull down. So you're going to be doing, there is enough evidence. Pick include. I'm going to abbreviate this. Women proportion bigger than men's proportion. But we've actually proved in this case that women are more honest than men, because they would return the money more often. Now, so far so good. Now, suppose I just give you an H0 and an HA, no story, just tell you. And the one I'm going to give you is P1 take away P2 is 0. P1 take away P2 is less than 0. And I just tell you what the z-score is. Now, if I gave you this information, the fact that they've given me a z-score is really all I need to do, because can't I now find the p-value? So what's the p-value going to be? It's the probability that you get z-score less than negative 1.7. Show you what that guy looks like. So I'm kind of doing this one rather than going through an entire story. So you've got a story, and in that story, here we go. Are you looking at the salt thing again, the window? Okay. So you're trying to prove that the first guy is less than the second guy, essentially. So that makes it a left tail test. And in a left tail test, you put the number negative 1.7. And in this case, the p-value is 0.044. Now, jumping back and forward, now that we've got that guy. Next one, I'm not going to jump back and forward so much. Right, that is essentially 4.4%. Now, in this question, I'm also telling you that alpha is 5%. So when you do the test, is the p-value less than the significance level alpha? Is 4.4 less than 5%? The answer is yes. But in these homework questions, all you do is have two choices. In one of them, you put the p-value down. And in this case, you would put 0.044. And then in the other, there are two choices. And the two choices are reject the null hypothesis or do not reject the null hypothesis. Right. Is your p-value less than 5%? Yes. If it's less than 5%, you always choose the reject the null hypothesis. The full sentence goes something like this. There is enough evidence to reject the null hypothesis, and so we can conclude that the alternate hypothesis is true. But rather than give you that entire sentence, they just gave you the beginning of it. Now, suppose that this was 8%, so the answer would be no, right? You would choose do not reject the null hypothesis. That would be the statement that you would finish with in that situation. Now, what would happen if we had a story where P1 take away P2 equals 0, and the alternate P1 take away P2 was not equal to 0? Wouldn't that one be the equivalent of saying that the two proportions are just different in some way? We're not specifying bigger or less, but just different. And let's suppose in this story, the significance level was 1%. And in this story, we did all the work and we got to 2.6. Right. How would that question finish? Well, we would find p-value. And this is where a not equal to gets a little bit weird. Because there are three versions, only one of correct. It could be this one, it could be this one, or it could be this weird one. Which of those three is the correct calculation for a not equals?
Is it the third option?
It is. It's the weird third one. We haven't done many of those. But whenever you have a not equals to, it's a weird third option. Isn't this, I'm trying to think of what they call it. I think they call it a two-tailed, don't they? This is called a two-tailed test. So I'm now going to show you how you would calculate this story, right? The 2.61 using salt. Well, I will eventually once I make my windows go away. Right, you over here. Oh, they call it both-tailed. Okay, that's fair enough. Both-tailed. And in both-tailed, you see you got a bigger than and a less than. So I'm typing in the negative 2.6 on this side. And then I have to kind of jump over to here and put in the positive 2.6 on that side. And the p-value that we get out of that is 0.009. So left tail test, right tail test, two tail test. Left tail test is when you want P1 to be less than P2. Right tailed is when you want to prove it the other way. And two tailed is when you want to prove that they're different in some way. So I'll return to here. And let's do our test. Is our p-value less than significance level alpha? Is 0.9% less than 1%? And the answer is yes. And when it's yes, you hit that guy there. Okay, before I move on, a couple of little tidy up things. If you get a correct answer, but WebAssign says it's wrong because there's a rounding off issue, I kind of need to fix that for you because you don't deserve, you shouldn't lose points over something that you've really done correctly. And then there is this issue, I guess I'll call it. This is the standard error for the difference between two independent samples. And we've been using it and it is correct. There are, however, because I discovered it today and I killed the question because I did it, there is another pooled sample. Now, when you do, and I'm just telling you this for completeness, I am not going to give you a test question in it or a homework question, but I just want to show you what I'm avoiding, just in case you come across it. In some circumstances, and it's not that clear in WebAssign which ones they are. So when I found this one, I killed it. So I hope I haven't missed one. But there are some circumstances that you can make an assumption, which is quite a big assumption. And that is that the two populations are connected in such a way that you can actually pull the data together to get a standard error of a pooled guy. And the formula for that is P hat, Q hat over N. So you might say, what's this guy look like? Can you imagine P1 was 15 people out of 50? And P2 was 23 people out of 40, right? Just for example. If you pull the data to get this guy P hat, you add the top together and you say 38 people out of 90. Do you see how they created the pool? And that's the only difference. The null alternate are the same. Once you use that guy as your pooled fella, it's still going to be P1 hat, take away P2 hat, but the standard error will be a different number. So when should you do this? I'm not quite, well, I know when you should do it, but I'm not sure when WebAssign should do it because I don't think they're the same. You can get away with this circumstance or this situation if the P1 and the P2 are the same size and they are essentially the same thing, like 100 people did something and then they got a pill and they did the same thing again, right? So it's the same 100 people, but there's a before and an after of them. That would be a situation where pulling the data might make sense because it's the same people, so you might expect the same kind of variation, right? That's really a very limited subgroup. Would you agree? A before and after with the same group of people is not the typical question that you typically deal with, right? But that would be a situation where that would happen. You can't just randomly assume that you can pull the data because you want to. In the one question I killed, it looked like that's exactly what they did. They just decided, yeah, we can pull the data and use a p-hat to calculate this, the standard error instead of this one. This one, by the way, is more accurate than this one. Secondly, see if you didn't pull the data when you should and you use this calculation instead, the two answers are virtually the same anyway, so it doesn't really make a lot of difference. So can you see why this is just a safer formula to use in pretty much every situation? And pulling the data is such a rare subgroup that I don't even want to dwell on it, because you know what's going to happen if I tell you you're going to do that instead of this, which would be a bad idea, right? It's much safer to just use the standard error the way we are. So hopefully I haven't labored that point too much, but if you notice one of your questions disappeared, that's what's happened. I just killed the pool data one. Any questions? Or are we good on hypothesis testing? Right, let's move on. We only have two more guys to go and we kind of know who they're going to be, don't we? So let's do a hypothesis test on a single mean. I'll give you a story and show you how it works. Let's pick one. A company collected data on 100 employees. And I have no idea where they got this data, and it's probably illegal to collect it. But for my story, they went and found out that their mean weight was, don't know, 200 pounds. Some time goes by. COVID happened. And they now have their new mean. And they found out that they put on some weight. So that might actually be true. I'm not going to ask you to share, but I will share. I am sure I have put on in the last year at least 5 to 10 pounds. I don't like looking at scales anymore because they depress me. And I am blaming COVID. And you might think, how could COVID be to blame? Well, let me tell you, if you ever saw me teaching at college, I stand up and I walk back and forward and I walk everywhere and I do a fair amount of walking and I'm not on my bum all day. Guess what happens when I teach now? I sit in my bum all day and I eat bags of chips because I get bored. And I drink far too much for this. So I have got some COVID weight, right? Do some of you, without sharing details, do you think that that is a real thing? COVID weight. Weight that you have put on because of COVID.
Most definitely.
Most of you going to agree with that? There is a COVID weight thing. So can we pretend that this is true data And now we're going to do a hypothesis test, and I would write a really cool article and get it published somewhere, right? If it was true data and I had collected it, right? So my null hypothesis and my alternate hypothesis. My null hypothesis is that the mean was 100 and it's still 100. And my alternate hypothesis is that the mean, oh, sorry, not 100, the mean is 200. So these people were already pretty big, right? And we've now said that they've probably increased. Do you remember that little Greek letter means the population mean is 200 and the population mean is now greater than 200? Because this company only has 100 employees, right? So that 100 is a population. So technically speaking, now that I've thought about that, I really should have called that 200, shouldn't I? And this is the new mean, so I'll call that X bar. Now, if it's going to be a hypothesis test, don't we need a significance level in this story? I'm going to pick a significance level of 1%, right? So if I get anything significant out of this, isn't this going to be like guaranteed that it's true, right? A 1% level, well, 99% true, I guess. There is one other piece of information I haven't given you yet, but I'm about to. Do you know what that piece of information is? What do you think is missing?
The Z-score or Z-score?
Well, that is missing, you're right, but something's missing even before that, Cheyenne. Something I need to tell you that will allow you to get the Z-score. I'm sure when I tell you, you'll say, oh, yeah, I didn't know that's what he was asking for.
Standard error?
Yeah. We don't know the standard error, do we? Agree? So you need to be told it, or you need to be able to calculate it, right? So what can happen in the story? Well, if I can zoom back to my window, I don't know where I am. Right, here we are. You were told, because I'm telling you, that sigma was 6 points. Right, so we know everything now, right? Sample size, technically it's a population size, but we'll call it a sample size. We've got a mean, we've got a population mean, population standard deviation, we've got a significance level. Here is our null alternate. Is that a right-tailed or a left-tailed? Agreed. I saw your mouth moving, and she said right. I need a Z-score.
Is your standard deviation 5 or 6? Sorry.
It's 6. I was going to make it 5, then I decided to make it 6. So it's 6. So I'm looking for a Z-score here. X bar, take away mu, over standard error of X bar. This is going to get some cobwebs out, yeah. What is the standard error of X bar? Sigma over the square root of n. So in this case, 6 over the square root of 100, 6 over 10, 0.6. So my Z-score is going to be 215, take away 200 over 0.6, which gives me 15 out of 0.6, which is 15 divided by 0.6. And oh, would you look at that for a Z-score? Now, I'm still going to go through the process. I wish I'd maybe made these numbers closer. Now, too late to change. I found a really big Z-score. How do I know, even although I've not finished the process here, how do I know that that's going to be significant? What's special about a Z-score of 25? I'm not going to wait for David to say it because he's the one that always answers this question. Someone else help David out. What would David say if the Z-score is 25? Why is that so important? Phrase it another way. What is the usual values that you expect Z-scores to be?
Is it -3 to +3?
And isn't this huge?
Yeah.
And that's what I was getting at. Right, so that's what my question was asking. This is huge. It's a big Z-score. And therefore, I know this is going to be significant, but I'm going to have to go through the process to finish it. So the finishing process is p-value. And the p-value is the probability that you get a Z-score greater than 25. Now, I'm not going to do that on SALT right now. Can you just trust me that the answer it comes up with is 0 and then it says error? Because it doesn't like numbers that small, right? Z-scores, expect with values like that. So then we do our test. And our test is our p-value less than the significance level? Is 0% less than 1%? And we are going to say yes. And we can conclude with a sentence something like this. That there is enough evidence to reject H0, which is a null hypothesis. And you would probably only get a circle with that guy and a circle not enough evidence, but there's another part to this sentence, and I feel it's necessary. So there's enough evidence to reject it, and so HA is true. And in English, we've just proved that COVID weight is a real phenomenon. People have put on weight, at least based on this sample. In many ways, isn't this very similar to the proportion one? It's got the same flow to it, just different kind of variables, right? It's not P, it's mu, and so on. Now, I've said something that's slightly unrealistic. In this case, the sigma has been given to you, right? And that's the population standard deviation. But that's really quite unrealistic. So here's another story. So we know somehow in the past that the average height of Scots was 62 inches. So 1,000 years ago, I mean, they've got some skeletons. You can measure the height of someone from their skeleton. And they found out the average Scots male was 62 inches tall. And I guess it'd be an anthropologist would maybe be interested in this. He believes that the typical Scots male of today is taller, right? So what he did is he collected a sample of 100 adult Scots, and he found out that their average weight was 64 inches, and that the standard deviation was 5 inches. Okay, now this is the standard deviation of this 100 sample. You can always get a standard deviation of sample, right? You can put it into a calculator, you can get it, right? You can't get the population standard deviation. Would you agree population standard deviations are almost impossible to find, right? Because you'd need to know every single person in the population to do that. So that means I'm going to have to adapt this a little bit to cope with this new information. So the null hypothesis is that the population average height of Scotsman is still 62, and that the alternate hypothesis is that it's bigger than 62. Right, that hasn't changed, right? Would you agree based on this evidence? He believes Scotsmen today are taller on average than they used to be. And now I'm going to find the standard error of X bar. I would have used the population standard deviation if I knew it, but since I don't know it, don't I just use this guy instead? Would you agree that's just a minor detail, right? You have to use somebody's standard deviation. So if you don't have one, you use the other, right? But that has changed something else. That is a Z-score. And the reason it's allowed to be a Z-score is because we're assuming that the population is normal and that we know sigma. What's going to happen here is that we need to use a T-score. And that is pretty much guaranteed in virtually every question you're ever going to do. But just in case they sneak one of these. Now the T-score is that guy. So it's actually the same formula. And in this case, it's going to be 64. Take away 62, divided by 0.5. And we get a T-score of 4. So now I'm going to get the p-value. But it's going to be the p-value is the probability that you get a T-score greater than 4. Now, one more thing I need if I'm going to use T-scores. I need degrees of freedom. Right? T-scores use degrees of freedom because don't T-scores use different numbers and we got to work on the different number thing, right? So what kind of degrees of freedom do you get when your sample size is 100? 99. So far, so good. Here's a new difference. We are going to use salt. We use salt to get p-values. If you remember doing confidence intervals, we didn't use salt, right? We could do it with a table and we just read the number off the table, right? But the world has changed. In hypothesis testing, you got to use salt. It's really the only, that's what I'm looking for. It's the only way that you can actually do these calculations, right? So I'm clicking this guy on. And I'm going to hopefully, right, I'm assuming nobody's going to come, so I'm just closing that window. If somebody turns up late, tell me about it and I'll open up one of my closed windows for them. Right, so here is salt. We want to know the chances that a T-score is greater than 4. Looks right, looks ready to go. It's not ready to go. You have to hit T-distribution. It's not a big deal, right? But you still have to make sure. If you do it in Z, you're not going to get the right number, right? Now, you see in T-distribution, there's a place for putting 99 degrees of freedom. Right, so you must, that's new, right? You have to put in 99. Now, are we wanting a left, a right, or a both-tailed? Well, this one was a t-score bigger than 4. Right, so bigger than 4 is left or right?
Right?
Okay. And you see how it's pointing the same way? So I can now type in 4. And the answer I got is a very small number, which looks very similar to another very small number I got for a totally different question. And so I'll click out of this fella and click into this one and show you what we got. We got this p-value, which is 0.006%. Oh, and I forgot significance level, right? So what we now do is we do our test. Is our p-value less than the significance level alpha? Is 0.006% less than 1%? And the answer is yes. And I'm not going to write that big long sentence again. Do you know the one? We can conclude that there is enough evidence to reject H naught, and so the alternate is true. And what we can say is that in this question here, isn't that evidence that Scotsmen have got taller today than they were in the past? And if you're an anthropologist, you could go into, isn't that interesting? And come up with reasons that I actually know this is true. Do you know that modern people are taller than ancient human beings are? And do you know, I don't know if you should know this, but does anybody know the main reasons that they give for why we're taller today than we were in the past?
Is it because we have like more food
Yeah.
for people? Yeah.
Yeah. That's the main reason they believe. Yeah. And it's actually quite a modern phenomenon. I mean, even just 200 years ago, which isn't that long ago, people were significantly shorter than they are today. Just a useless piece of information, but it's true. And we believe it's to do with nutrition, especially nutrition when you're young. I mean, if you get a lot of food when you're young, you'll probably be quite tall. If you deprive a child of good quality food when they're young, they tend to be shorter.